Hello everyone. Today we're going to start or continue looking at exponents and different cases and work our way towards rational or fractional exponents. I just want to take a few minutes, however, to start by talking about what happens if you have negative bases. I believe we've discussed this before, but just to make sure you have like a note or a video that explains this as well. I think it's important to go through this. This is the case where some of your calculators won't even do this right because calculators tend to have a negative button and a minus button, which are two different buttons. The negative button is supposed to assume that there's a bracket around the base, as is shown in this example here. If you use the minus button, it's technically supposed to show this case, but some calculators I've seen, they just behave in a different way, so you got to be a little bit careful. So what is the difference between these two statements? Well, if you actually calculated this the proper way, the answer for this one would be -4, and the answer for this one would be +4. And the reason is that the bracket tells you that the negative is part of the base, or the minus sign is part of the base. But in this case here, the minus sign is actually considered outside of the base. It is not being affected by the power. So what -2 to the power of 2 means when it doesn't have a bracket is it actually means the negative of 2 to the power of 2. So it's like a -1 here that's multiplying the 2 to the power of 2. And in BEDMAS, you do multiplications after you do powers. So it can be a little bit tricky when you're dealing with situations like that. So let's look at this scenario here, where I have -2 times a to the 3 all inside a power of 2. Well, when you bring the power in to the bracket, sorry about that, you've got to be careful, because which scenario do we have from above for the -2? Do we have the -2 outside of a bracket with a power of 2, or do we have a -2 inside the bracket with a power of 2, like this one? Well, as you can see from the answer that I've already written, it's the second case. The -2 is considered inside of a bracket. And remember, what does all of this mean? It means all of that base, there are two of them multiplying each other. So that means it's -2 times -2 and a to the 3 times a to the 3. So you technically are supposed to put the -2 in a bracket before you square it. So that would become 4a to the 6, which I'm not going to write the answer for. Okay? Then there's the problem of what happens if your bases have exponents that are positive, odd values, and what happens if your bases that are negative have exponents that are even values. And we've discussed this before, so again, I just want to go over it one more time. Anytime you have odd powers with negative bases, your answer is going to be negative. And that's because you have an odd number of bases multiplying each other. So you'll have -2 times -2, which will give you a positive, and then you'll have an extra -2 multiplying that's going to change the sign to a negative. So you should be able to visualize 3 negative numbers multiplying. 2 are going to group up to give a positive, and then there's going to be 1 left over. With a power of 5, same thing, same idea. You're going to have 4 that are going to group up to give positives, and then the 5th one is going to change the sign back to a negative. So when you have odd powers and a negative base, you're going to end up with a negative answer. If you have even powers with a negative base, you're going to have a positive answer. These are concepts that you've probably seen before. And we're gonna see that that comes into play when we're dealing with scenarios like this with rational exponents, which I'm going to do next. Okay, so how does this lead us to this? So, rational exponents. Now, what is a rational number? I've written it here as a fraction that makes sense. So any number that can actually be written as a fraction, so 2/3, 4/7, all of those decimal values are fractions that quote unquote make sense. They're rational fractions. A number that isn't rational would be like pi. Pi is considered irrational because you can't write it as a fraction. There's no fraction that gives the number pi. Okay, so because pi is a number that continues forever. So we want to look at rational exponents. So rational meaning fractional powers. Okay. Now, anytime you consider something like this, please be careful on if you actually wanted to input this on a calculator, you definitely have to put a bracket around there, which I'm going to start using a little bit more later on. But what does 2 to the 1/2 mean? And we investigated this a little bit when we were doing exponentials. And the easiest way to show it is just to do a bunch of examples. So if you do the square root of 4, okay, now the answer is usually +2, but technically there are 2 different answers if you're solving an equation, okay? But if you do 4 to the 0.5, it gives you 2. It's the same answer, okay? If you do square root of 9, you get +3. If you do 9 to the 0.5, you get +3. Does this work for cubics? Well, if you do the cube root of 8, you get 2. If you do 8 to the 1/3, you also get 2. So a pattern seems to be emerging here. What is that pattern? Well, it seems like in general that if you have a number like a to the 1/n, that the n, which is the denominator of the fraction in the exponent, is going to be the type of root that is surrounding the base, okay? So why do we need to know this? Well, the issue is that a lot of calculators unfortunately don't have an n root button on them, although newer calculators tend to have an n root button. Older calculators don't. So if you had to do like a 4th root of a value, older calculators wouldn't be able to do it with a root symbol, but any calculator can do a power that's a fraction. So any root type can be written as a fractional exponent and then be done on any calculator. And there are other benefits to it too. It does help in certain scenarios to be able to do this, which I'll show later. So if I ask you to do 3 to the 1/2, I could ask you to write this in radical form, okay? So write as a radical. The word radical means root, okay? So if I ask you to write 3 to the 1/2 as a radical, you'd look at the denominator of the fraction, and that is the type of root. But with a square root, we normally drop the 2, okay? Because the word square is referring to the 2, all right? If I ask you to do 3 to the 1/8, again, what is the type of root? The 8 is the type of root, okay? So the denominator is always the type of root. So what happens if the top number of your fraction isn't a 1? So all of the ones we've seen so far, the top of the numerator of the fraction has been a 1. Well, how could we rewrite this in a way that would explain how to actually find the answer? So our base is 3, right? I could write this as 3 to the power of 1/7, all cubed, because we know that the rule for an outer power and an inner power is to multiply. And when you multiply, it's top times top, bottom times bottom. So this is the exact same thing as this. Well, if I write the 3 to the 1/7 now as a radical, the type of root is the 7, and then I have my outer power of 3. And this is actually my preferred way of doing this. There is another way. When you have an outer power of 3, so what's the other way? Sorry, let me explain this. Or we could have also done 3 to the 3 to the 1/7. And what that would look like would be the 7th root of 3 to the power of 3. So both of these are interchangeable. I don't like the second one. I almost always exclusively will use the first version. I don't know, I just prefer to see that it's an outer power. The inner power just bothers me. But it really doesn't matter which way you do it. So if I asked you to calculate this, how would you do it? Let me get rid of this window here. So, does your calculator have a 9th root button? Or does it have an X root button, right? Now, even if it does have an X root button, I still feel like it's faster to just rewrite it as a power. So it would be 57. And the type of root is the denominator of the power. And the outer power is the numerator of the power, okay? And if I put a bracket around that, I could just type that into my calculator, and 57 to the power of bracket 4 divided by 9 bracket, and that'll give you your answer, which I'm going to allow you to figure out on your own, okay? So if you have an X root button, sure, you can use that X root button. But I personally will always transform these. Even if I have an X root button, I just find it easier to type in my calculator this way, and I find it faster. So this is an interesting case. We talked about negative bases earlier. And remember, when you have a negative base, technically if this was an x up here, it wouldn't be considered an exponential, but you can do it mathematically as an exponent, okay? So you can have negative bases. So we have to talk about the fact that when you have a negative base, and if you have an even power, the answer is positive. If you have an odd power, the answer is negative. But here we're talking about roots, right? This power of 2 over 3, the 3 is telling us what kind of root. So can you cube root a negative number is basically what's being asked. So if you write it as a radical, you would have the cube root of negative 2 all to the power of 2. Okay, and you can cube root a negative number. This is not going to give us a nice value, but you can actually cube root a negative number. And so if you type this into your calculator, you should get an answer, okay? But what about this one? So here, we'd have the square root of negative 2, all to the power of 3. This is, that's an arrow, sorry. This is complex, right? You would have an I show up because you're square rooting a negative number. So the denominator is important, especially if you have negative bases, because if the denominator is even, you're working in the complex number system. But if the denominator is odd, then you're fine. Okay, so you be wary that you may end up with errors when you try to do something like this if you don't realize that an even base will give you a complex number. So on page 215 of your textbook, so let me call up your textbook here. as we've discussed before, in math textbooks, there's often a summary or a key concepts area. This is on page 15 of your textbook. We're in section 1.2. Okay, here are all of the summary information about what we've basically been talking about, written more mathematically. So a to the 1 over n is equal to the root of the nth root of a, where n is a natural number. So natural number meaning positive values. So the reason we want positive values here is if we had, and we'll talk about this in a second, what would happen if n was negative? Okay. So anyway, we'll talk about that in a minute. To evaluate a to the 1 over n, or the nth root of a in the real number system, if n is even, then a has to be greater than or equal to 0. So we were just talking about that. If n is even, then the base has to be positive if we're in the real number system. Okay? But if n is odd, then a can be any real number. The base can be any real number at that point. And then they show you what happens if the numerator is not 1. And then they talk about how you can do this with pencil and paper. Okay? So the key concepts in your textbook kind of go over all of the things we've just talked about. Coming back to our note here. So I was talking about what happens if you have a negative exponent. Well, this is a combination of some of the exponent laws that we've previously seen. When you have a negative exponent, that flips that base upside down. If it's in the numerator, it goes to the denominator. If it's in the denominator, it goes to the numerator. So in this case, it's in the numerator. It comes down to the denominator, and then the power becomes positive. And then we would write it as a radical. Like so. Which you could then do in your calculator, or you probably could have done it on your calculator this way better actually, but if you're asked to write it as a radical, you do this. So I can ask you to go back and forth between these two forms, and there'll be an assignment coming up that'll probably ask you to do that. So one last thing I'd like to talk about is what happens if you have roots of roots. I kind of hinted at this the other day. So let's say you had the fourth root of the fourth root of 3. Okay? So it's a little bit, you know what, let me change this to an x actually, because you could just probably do the fourth root on a calculator on certain calculators, but if it was x and I asked you to write this as an exponent, okay, so write in exponent form, right? Well, let's write the inner one first as our exponent. And this is where I like to think about oysters and pearls. So my pearl is x. X is trapped inside of an oyster, and these are the two shell pieces of the oyster here, okay? And the type of oyster is a 1/4 oyster, because when we're taking a root and writing it as an exponent, it becomes a fractional exponent. But then we have this other outer oyster that ate that inner oyster. So here's my inner oyster. I'm going to use a different color for the outer oyster. So that would be this here, okay? It also has a power of 1/4. And now we have a scenario where we have a power of a power. And I kind of didn't want to give the answer away last time we talked about this, but when you have a power of a power, you multiply the powers. So you'd have x to the 1/4 times 1/4, which you can do in your head. I'm just going to write it out here, which gives x to the 1/16. Top times top, bottom times bottom when you're multiplying fractions. Okay? So even if you had different roots, so let's say you had, let's say we had the cube root of the fifth root of 3x to the 5. Let's do 3x to the 7. Okay, you could have any kind of Perl you want in here, right? So I'm just going to put the Perl in a bracket so it's a little bit easier to see that that's our base, all right? So you can work your way inside out. So let's do the inner power first, or the inner root, I should say, first. So that's a fifth root. So that's going to become a 1/5, right? And then you enclose that in another bracket and do the outer root, which would be 1/3. Right? And let's propagate this. So we'd have 1/5 to the 1/3. That's a power of a power. So we multiply top times top, bottom times bottom. So that gives 3x to the 7 to the 1/15. And if we wanted to go even further in a case like this, we could then apply the outer power to all the inner powers. Remember that the 3 has a power of 1 there, so that would become 3 to the 1/15 and x to the 7/15. And that would be writing our answer as an exponent form instead of radical form. So I'm going to finish the lesson there. There will be homework assigned for this lesson. If you have any questions, please email me, and we'll talk about how to fix those problems. Have a great day, folks.